Week 10, we continue GPIO. Let me briefly talk about what I'm going to be talking about this week. We are going to continue GPIO, so it's going to be like a recap of what we've been talking about the previous week. So we are going to make a summary of what we tried to do. However, while we're doing this, we are going to extend the configuration of the GPIO such that it's not only going to be LEDs, but LEDs plus switches. So we are going to initialize the port, specifically port F, not only for an output device like LED, we're going to initialize it for both input and output. So we are going to be able to use both the LEDs and the switches, which are on the card. Okay, so I think you got the idea if you've seen the previous week's lecture. Let's continue. Okay, so the switches, we'll talk about the switches. And remember that on the cards, we have the switches here and here. This is switch 1. This was switch 2. And this was the reset switch. So be careful, guys. Actually, you've got 3 switches on the card. These ones are the switches which are connected to PF4 and PF0. So this is connected. As you remember, switch 1 was connected to PF4. If you look very closely, you will realize that there's a cable going on like this, if you can follow my mouse cursor, and it's being connected to PF4 here. It's PF4, this pin is PF4, this pin is PA2. And this one is connected to PF4, this one is connected to PF0. And this switch is not connected to this part of the card. It is connected to this microprocessor here, because this microprocessor is the microprocessor that controls this. It is used for resetting. So if you have a code, if you press the reset, the code will restart again. The mechanism of reset is something related to interrupts, which we are going to start talking about next week. So remember that when I say switches, I don't mention the switches here. This is the reset switch. That has a purpose. But these ones are the switches that are connected to the port F, which we will be using. Okay, PF4 and PF0. Okay, so the switches and the LEDs and their schematics to which pins they are connected to. This is the device, I mean, figuratively. And to PF0, I have switch 2 connected. To PF4, I've got switch 1 connected. And to PF1, 2, 3, I've got the RGB LEDs connected. Okay, good. And some other devices like serial ports or USB connected to other ports, they're also being shown here for, I don't know, to give some information. About the serial port, we are going to learn this in this course, but we are going to be using serial ports in the next semester's course in embedded systems. Okay. Now, there's one thing that we should definitely remember and talk about, that these ports are separate circuitries on the device. So on the device, here on the device, this is the microprocessor. So it has the arithmetic logic unit somewhere. It has got registers somewhere, very small. And it has this digital pad, 6 of them, somewhere here, okay? So this is actually a part of the circuitry of the microprocessor's architecture. And this architecture is flexible. I mean, this circuitry, which we call the digital I/O pads, is a flexible architecture. Why I call it flexible? Because you've seen that we can change the purpose of the functions of the pins. We can make them input pins, we can make them output pins, we can make them digital pins, analog pins, and they even have some alternative functions we don't know how to use, and we will not learn how to use in this course, but we will learn in other courses. So a very flexible architecture. And if you have a flexible architecture, if you have a flexible digital pad in an architecture, it means that you can change the purpose of that pad using some control registers, because there are no other ways to do it in computer engineering. If you have a function, multifunction flexible pad with many purposes, to use those purposes, there are certain control registers. You tweak them, you change their bits, and you use them for different purposes. And actually, we have gone over this. We have manipulated some of these registers so that we were able to use some pins of port F as output pins, and those pins being connected to the LEDs, RGB LEDs, we were able to make color, if you remember so. Okay. So remember that each port is a separate hardware instantiation of a physical block circuitry. Instantiation is you've got something, you clone it. So there are clones of this pad. There are multiple pads. So don't make this mistake. I mean, this pad works for all I/O. No. For each port, port A, port B, port C, port D, port E, port F, 6 of them, we have separately 6 different digital pads circuitry inside our architecture. Okay, and they've got specific registers. Some registers are used to read data. Some registers are to enable that port. Some of them to designate the direction of that port, input or output pins. And in the end, the most important register was the data register, because we used to write or ignite the LEDs to make the LEDs bright. Because when we write to this register, the data register, if we make the necessary configuration, we were able to change the output pins which were connected to the LEDs and thus change the colors of the LEDs. Okay, pretty much a summary, I guess. So I'm doing the summary just one slide earlier always. This slide is saying the exact same thing that I just said. So by reading and writing to this memory location, when you have the necessary configuration, you're able to read and write from the pins which are connected to this device. So this is general purpose input output. So when a device, it could be a LED, it could be a switch, or it could be a more complicated digital or analog device. When we have those connected to our system, actually what we can do is we can just make this GPIO, general purpose input output operations, by reading and writing from this register. And however, just like we said, before being able to do this, there are many initialization, configuration steps we have to complete. And these configuration steps are all about changing the bits of some control registers depending on the function that you want to initialize to some certain values. So you change the bits. That's the story. And actually, I tried to tell you this the previous week. This is the story. I mean, this is a very simple card, not a very simple card. You can do many fantastic signal processing stuff with this card, but there will be cards that you'll be using, FPGA cards, if you become hardware programmers. Whatever complicated, different cards they are, one thing won't change. You'll have a microprocessor. You're going to write codes that will run on the microprocessor, be it assembly codes. They could be C codes, embedded C, which you will see in the next semester's course. Or there are some platforms you write Python codes, and the Python code is directly loaded as the machine code to the card. So from Python code, compiled directly to machine code. Whatever platform, whatever language you do, one thing won't change. On that card, there will be different circuitry which have different functions. And to use those functions, you will have to change some control registers of those functioning circuits. There will be a pad for serial communication, and you'll open the data sheet. There will be registers for that serial communication, and it will say, if you change this control register, you'll be able to send 8 bits of data in frames, and it will explain. So actually, hardware programming in very general is all about understanding those functions by understanding how to manipulate these control registers that belong to that functioning digital pad. Okay, that's pretty much a summary, I guess. Any questions? Guess not. Okay, mute. I'm muting somebody. Okay, now, as I said, this week, the new thing to do was to introduce the switches. And the switches are, switch 1 and switch 2 are already connected to PF4 and PF5. And on the card there, if you see can you see my cursor, mouse cursor on the screen? I hope so.
Evet,
but they are here. So this is switch 1, this is switch 2, because I'm going to press those switches. I'm going to get my finger there. I'm going to press those switches in.
Hocam galiba göremiyoruz.
You cannot see it. Okay. So
az önce görülüyordu da şu an.
Okay, then I'm going to move my finger there then. Okay. So this is switch 2. This is switch 1, guys. Okay, so it could be a bit strange for you, but it's, yes, this is switch 1, and this is switch 2, and this is R2D2. Okay, so and we have got the LEDs. We are going to be using the LEDs as well. I mean, so we are going to make codes which will get inputs and provide outputs accordingly for the first time. Okay, so I'll get to the initialization again. This time I'll try to make it a bit quicker, but the thing is, this time we are going to initialize the card not only for LED operation, which means not only for configuring 3 bits for input, but we will initialize the card, the port F, such that we'll be able to use these ports, these pins, PF1, PF2, PF3, as outputs because they are connected to the LEDs. Plus, we'll be configuring PF0 and PF4 as inputs because they are already connected to the switches. Okay, so I'm going to be doing the initialization once and for all for both of them. That would change things because if you remember in the initialization procedure that we've completed the previous week, what we've done was we have changed the bits which correspond to only PF1, PF2, PF3, because that was the only operation we did. But this time we'll need to use the switches as well. So we'll need to configure these pins as well. So remember, guys, in this architecture, that could be different for a card, but in our architecture, to use some pins of a port, the initialization is usually pin-wise, which means you do it for each pin separately. So when you change a bit for a pin, you can use it if you read the data sheet. But if you want to use another pin of a port, most probably, and it's always the case in our control registers, you'll have to change the necessary bit which corresponds to that pin for that control register, I mean, whatever control register you're working on. Okay, good, good. So this was the initialization procedure, which was executed only once at the beginning. And it's pretty much similar, but we've got new steps. Let me get there. So the first one was, remember, I mean, this is a very nice slide because it shows which initialization steps are different compared to the only LED initialization. Well, the gray one here, the first one, does not change because whatever we do, we'll have to feed clock into this digital pad. This doesn't change. Well, the blue ones are new. The blue ones were the ones which we've skipped the previous one. We did not do. So these were not done in the previous one. In this one, we'll add these steps. And the red ones are, you had those steps in the previous one, but because you are configuring not 3 bits, but 5 bits in total, the values that we assign to the registers will change. So we had those steps, but we will modify these steps. So the red ones are the modified ones. The blue ones are the added ones in this case. And the gray one is the one that won't change. Because remember, we have fed clock to port F, to whole port F. It was not a pin-wise configuration. Okay? Okay, so this time we are going to be doing this print. So these will be changing. Blue ones added, red ones modified, and the gray one the same. Okay, let's see how it's done. Okay, the gray one. I start with the gray one, which was feeding the clock. This is feeding the clock, guys. And it does not change. It does. Allah'ım ya. Abi çok ilginç bir şekilde sekreter beni hep derste arıyor. Hiçbir zaman da aramıyor. Bir saniye, önemli bir şeyse açayım arkadaşlar. Alo? Ha. Ya aslında dersteyim Dilek Hanım. Tamam, görüşmek üzere. Allah'ım ya. Sitcom gibi oldu da. Neyse, şimdi kadın YouTube'dan izleyip neyse, boşver. Okay. What were we talking about? Okay. This one we were talking about. Well, yes. Do you remember the initialization procedure? I mean, if you don't, please visit the the previous YouTube video in which we have explained this, because actually we have gone to the data sheet, which was page 340. You can do it yourself as well. I'll try to remind you that if you remember, this pin was, so this was this sys control blah blah register was a 32-bit register. A 32-bit register. So this bit being the 0th bit and this bit being the 31. So the first 6 registers were used. So this 1, 2, 3, 4, 5, 6. And the rest was called reserved. Remember reserved. Yazamadık. Reserved. Okay. And if you remember, we have applied 0, 0, 0, 0, 0, 1 to these places, which would make the number, this bit, being, because the reserved bits are automatically 0, 2, 0, because this is 0 and this is, so being zeros, this is hexadecimal 2. That's why we have this number. So actually this was for port A, port B, port C, port D, port E, and port F. And by feeding 1 to this pin, actually we have enabled the clock feed to port F. That's why we were loading 20 to this register. Okay, and how did we do it? Actually, in my directives, I had a code like systic control blah blah EQ some value, which was 400 something something. So R1 is pointing to that location, which is the control register. So R1 is pointing to this register. And first I read the context of the register to R0. This is in this direction to R0. I OR this R0 with this value and write it to R0 so that this bit becomes 1. The others don't change. And in the end, I write it back to where R1 points, and it's being written to here. Now, since the pin, the 5th pin starting from 0, which corresponds to the clock being fed to port F, is 1, now I'm feeding clock to port F. And in the datasheet, it said wait for 2 cycles and do nothing so that the digital pad can get its breath and start working. Okay, this was the idea. This step does not change because we have initialized port F all in once. There was nothing defined bitwise in this step. So we don't have anything about a certain bit of port F. We just feed clock to port F in total or not. That's why, since we are going to use only port F again, because in the previous example, we have used 3 pins of port F. Now we are using 5 pins of port F, still port F only. This step does not change. I guess there are no questions about this step, right? Questions? Okay. Good. So the next step is a new step, guys. In the next step, we do some operations. And it's a bit strange operation, guys, because in this step, we unlock PF0. PF0 is already connected to switch 2, remember? So let me show you again. PF0 is connected to switch 2. And in this device, PF0 is by default so-called locked. Well, this is something new. I understand. I mean, why it is locked? Many questions here, right? Why PF0 is locked? Are there any bits that are locked? Which bits are locked and which bits are unlocked by default? Well, I understand. Those are good questions, I mean. But apparently, the guys who have designed this card by default locked these 2 pins, PF0 and PD7. So if you want to use these 2 pins, you have to first unlock them. How to unlock them? In the datasheet, the procedure is clearly explained. And actually, I won't open the datasheet so that you don't have, I mean, it will be easy for us because I've provided the details of the unlocking mechanism in these comments. So to unlock these 2 pins, what we have to do is first to change this register, this so-called register, guys. Okay. But to change this register, frankly, the architectural mechanism I mean, once you requires you to do something beforehand, which is to change register this word. So, but in order to change this register, we have to do something else before. So before being able to change this register, you have to change this register, guys. It's another register. And you have to write these values to it. Why these values? Well, you can go into the datasheet, read this datasheet's details, and which pins are 1, which pins are 0. It will make sense to you. But what I do is, I get this value to R0, and I write this number to this lock value. Then I can change it. Then I get this value, point to this register first, and I write these values to this register, guys. So first the lock register, then the control register. And after you do these operations, you'll be able to do operations on PF0. Well, you might say, well, this is something, I mean, how should I know this? Well, you're not supposed to know this, but it's written somewhere in the data sheet. So if you did not know this mechanism and just try to work on switch 2, you won't be able to do it. So the important question is here is, I've got a new card, I want to use some pins of it, and there's a initialization procedure that I don't know how. Well, the only way to learn how is to go and read the data sheet. I know it's thousands of pages of long, but you need to. That's the way it is done. I mean, when I was first preparing this course, I had this problem. I tried to use switch 2. I went mad. I always asked myself why PF0 is not working, why PF0 is not working. And at some point, I came across this lock mechanism in PF0, and I just put it. So that's something I love to remind students who want to be embedded programmers or work on embedded systems. Guys, embedded systems is a bit pain in the your back, I should say, but it's so valuable. I mean, embedded engineers are, I mean, they find jobs everywhere in the world. It's a very valuable job, but it's a hard job, guys. You have to be reading data sheets and just watching new cards and blah, 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 blah. Okay, so that's an example of why it's difficult. This card. Okay, good. We continue then. So actually, the step that we skipped the previous time because we were not using PF0, we did not skip this time. And this is the procedure. So yeah, in order to get these, we've got these, as you can see. So the numbers are here. Okay, so the next step is disabling the analog mode selection. You remember that one? What we've done previously for output only previous week. This is for the previous week. We have cleared these bits. This is bit clear. What does bit clear do? It checks the bits. So it just checks the bits 0, 32 zeros, and 1, 1, 1, 0. So since these are 1, it's going to make those bits 0. It will not touch the bits which have zeros. Okay, so this is bit clear, works with mask and checks the ones. So we have cleared these pins because these pins correspond to PF3, 2, and 1. Okay, but this time I'm going to be using PF0 and PF4 as well because I want to initialize my switches as well. And switches are, in our case, also digital devices. I'm going to make an analog mode selection. I mean, I'm going to deselect the analog mode for them. That's why these should be 1 as well in our case. So the number that I should be loading to this register shouldn't be E this time, but it should be 0, 1, 1, right? Because 0, 1, F. I'm sorry, 0, 1, F. Because this is F when this is 1, and this is 1. So it's 1F. So in this initialization procedure, the way I'm going to modify it is instead of 0E, I'm going to be doing 1F. So if you see, just instead of this, I'm going to be writing 1F. And this time I'll be clearing all least significant 5 bits from PF0 to PF4. Now I've got analog mode deselected for all PF0 to PF4. 5, the least significant 5 bits of port F, 5 pins of port F. Any questions? Okay, so
Hocam,
please.
tam olarak bu işi neden yapmıştık?
Analog, are you asking analog mode selection specifically or the initialization?
Bu şu an yaptığımız.
The analog mode selection. Well, our pins can be used as analog or digital pins. We should first understand what is the difference between analog pins and digital pins. Analog pins are types of pins that can be connected to analog input or output devices. And digital pins are pins that can be connected to digital input or output devices. A digital output device is a LED. A digital input device is a switch, for example. What is the difference between an analog device and a digital device? The main difference is, guys, analog devices have a wide range of voltage and current capacities. So when you have an analog device, the device that you connect your circuit to, because you're connecting a part of your circuit in our microprocessor, the digital pad, to that analog device, so much current can come and go. And that's a risk for your card because your card's architecture has some current limits that it can bear. Otherwise, it will burn. And if you're going to be connecting this card to an analog port, this card has some protection circuitries inside. So if you select the analog mode selection register, it will activate those protection circuitries so that the analog device which you connect to will not harm the device. But when you make that selection, digital devices which provide very low current values, low voltage values, will not function properly. That's why you decide to which pin what you are going to connect. And if it is a digital device, you have to tell the card beforehand so that the card's necessary connections will be configured accordingly. Is this an explanation for you?
Evet hocam, teşekkür ederim.
Actually, you talked about this the previous week, but I'm glad that you asked again. So that's mainly why. But one thing plus, I mean, you have all the right to ask, why are we doing this? Because that's the best question that you can ask in life. And ask it, please. However, there's something that I want to remind you. If you become some embedded programmers or hardware programmers, there will be cases that you're going to apply some initialization procedures, long initialization procedures, changing 50 control registers maybe, which you won't totally understand because it says in the datasheet. What I'm trying to say is, it is good to understand the architecture so that you do your operations quite correctly. However, in some cases in real life, you will not have to understand the architecture totally. You will follow the procedures, the initialization procedures written in the datasheet. You follow them, and you will see that the card is working for your purpose. So it is good that you ask your questions and understand, but in most cases in hardware programming, you don't have to totally understand every detail of the architecture. You just follow the procedures in the datasheet. Okay, just keep this in mind. Any other questions? Okay, good. Good question, thank you. So the next step was this one, it's red, which means we had that step previously, but this time we are going to alternate that step. We're going to modify it. Remember, this was the first step. Remember, this was. Because in this step, to enable the pins of port F, we have made entire nibbles, 4-bit pins, totally one. So we have written 1, 1, 1 to the first nibble. This is nibble 0, this is nibble 1, this is nibble 2, kind of. To enable the second, I mean, the first nibbles from left. So this is PF1. So when I say second, I started counting from 1. Maybe I should say first and second and third nibbles from left, starting from 0. From 0. But this time, I'm going to initialize. So this was for PF1, this was for PF2, this was for PF whatever 3. But I will, in this case, I'll have to make these ones F and this one F as well. So that's why I'm going to change the initialization procedure accordingly. How? As you can see, I'm clearing those bits. I'm not putting them 1. I'm sorry. This was a mask. So I maybe just misguided you when I said 1, 1, 1. This 1, 1, 1 mask is to show you which bits to clear. What I'm going to do in this step is, since I'm going to make these nibble zeros, this nibble zeros, this nibble, all of them zeros, I'm going to clear the entire register to make them zeros. In this case, I'll be enabling these nibbles as well, but I don't care. I'm not going to connect anything to them. I don't want to write a long code. That's why what I do is I load zeros to entire register. Now everything is 0. So the alternative function for all pins of port F are disabled because this control register is deciding that the pins of port F are used as general purpose input output, not alternative functions. Just it's in the datasheet. So instead of clearing those nibbles one by one, I'm clearing all the values in the register. So it serves my purpose.
Hocam bir şey sorabilir miyim izniniz olursa?
Please.
Hocam bu big R0 hani clear bit demişiz ya, clear the second, third and fourth nibble from left demişiz ya. Bu hangi satır geliyor? 1, 2, 3. satır hocam. Mavi kutunun içerisindeki 3. satır. Hocam oraya clear demişiz. Hani 2., 3. ve 4. yerleri temizliyor demişiz de.
No, it's all together. This line is talking about all these lines. So not that line only.
Ama hocam 111 yazması temizleyebilir mi?
Okay, well, bit clear. We haven't done nothing about bit clear, and the last thing in this hour, let's do bit clear, guys. Let's do bit clear. Okay. Okay, you're right to ask this question because I've explained bit clear to you, but you have never seen bit clear in progress. So I'm going to just show you that so that it will become clear for us. Let's say F. Okay, let's say B. Yes, I think this code is okay. So guys, I think do I have errors? No, I'm going to load it. Okay. So it's simple. I mean, in R0, I've got this value. So if I have this value in R0, what I have is I'm going to write the pins. So in R0, I'm going to write in binary zeros, 1, 1, 1, 1. Everything clear about this?
Yes.
I'm going to be doing bit clear operation. Bit clear operation is you again have a 32-bit. Actually, if you don't have 32-bit, it will just pad them with zeros to the most significant bit. So this is A. What is A? A is 10. 10 is this, right? So as you can see, I've defined this as 0. This has no different than writing. These are the same. Okay?
Okay.
So I'm going to do bit clearing. What does bit clear do? Bit clear. Bit clear looks at the mask. Okay? If the mask is 0, that pin, it does not change the corresponding pin. Does not change. Does not touch the corresponding pin. If this is 1, it makes that pin 0. So after this operation, since I have 1s only here in the mask, the corresponding pins will be 0, guys. So R0 will be, the new R0 will be 0s, 0, 0, 1, 0, 1. Okay? which
Hocam o
is
zaman bu bit clear
hexadecimal 5. Sorry?
Bu bit clear dediğimiz şey NAND mi oluyor dijitalde?
Well, we can say no, NAND. Is it NAND? Is it NAND? It's not exactly NAND. It is, because if you make a AND operation and NOT operation, let's make a AND operation and NOT operation. Well, let's see that this is the result, and let's try NAND afterwards. Okay. So I just going to press F4 and R0 become 5s. Okay. Here you can see. Any questions about bit clear first? No, I guess. Is it NAND? Well, you may be right. I just cannot remember if it was NAND or not. Let's make a NAND operation between these two values, guys. NAND, as your friend says. NAND is AND plus NOT. First, the AND, be careful. It is not NOT plus AND. It's AND plus NOT. Let's make an AND operation. AND, sorry, not a plus operation. AND operation. So it becomes 0, 1, 0, 1. But be careful. I'll do the rest of the operation as well. So this is 0, 0, 0, 0, 0, 0 equals 0. Now, are you ready to do the NAND operation, not operation? So, sorry, 1, 0, 1, 0. It looks okay, right? But these are ones. So because of these ones, they are not the same. Okay?
Okay.
Okay, good. But it resembles NAND. I understand your point. For the values 1, it behaves like NAND, but it's not NAND. Okay, so I'll just stop my debug. Good. Good. Let me get back to the slides. Here, I see. Okay, so instead of this, we have cleared all the bits. I've moved R0 to R0. I moved zeros to R0 and write it over it. So we've got those pins cleared. So the third step, let me just continue with this one and then give a break. Now, guys, this was the previous one. Why did we do this? Because we've checked the data sheet. And if you remember in the data sheet, this register was something like, if you just go to this register was something like, let me write the 32-bit values. First 8 pins have some values. Let me just share. These are reserved. And if these pins were 1, they were output. If these pins were 0, they were input. Okay? Since PF0 is connected to the LEDs, we want these pins to be 1. And we did not touch the other pins. And if you want these to be inputs, we'll have to make them 0. So actually, we have loaded 0E previously, but we are going to load 0E again previously because these are inputs. And for inputs, we provide zeros. So that's why we don't change. We don't make any changes. I made it red, but maybe I should have made it gray because we don't make any changes. Okay. Did anybody get why we did not make any changes? Do you remember the nature of the control register? Any questions? Okay. Okay, let's give a break arkadaşlar. Şunu durdurayım.